So we've been talking about the effects of magnetic fields. If there magically seems to be a magnetic field created somehow, we've talked about the force exerted on a moving charged particle, we've talked about the force on a current carrying wire, and then we've talked about some effects of that. And that's the last couple of days. But now we need to talk about where magnetic fields come from. What is the source of a magnetic field? So we're going to talk about 3 different sources of a magnetic field. So just like only moving charged particles can sense a magnetic field, feel a force, only moving charged particles make a magnetic field. So if you have a moving charged particle, it makes a magnetic field according to this equation. New constant, mu naught, I'll talk more about in a minute, divided by 2 constants you already know, 4 and pi. Isn't that interesting? And then QV cross R hat, I'll explain that in a minute, divided by R squared. So the first thing I want you to notice about this is that there's some numerator stuff, there's some constant stuff, and then it's distance squared on the bottom. So this is not that different than electric field from a point charge. Electric field from a point charge falls off as a distance squared. Magnetic field from a point charge falls off as a distance squared. The faster it's moving, the stronger the magnetic field it makes. And then we have this cross R. This is to get the direction. And it's going to go into the right-hand rule. I'm going to deal more with that later, so just ignore it from now. But this is the unit vector radius, because the distance dependence is the bottom. So if you were plugging into this, you would ignore this part. You do mu naught over 4 pi times QV over R squared. We'll deal with directions in a minute. So the other thing we need to deal with is mu naught. Mu naught is called the permeability of free space. You might remember that epsilon naught, which shows up in K, was called the permittivity of free space. So historically, people didn't believe that outer space could be a total empty vacuum. They thought it had to be something there, and it was called the ether. And that ether had different properties depending on if you were talking about electricity things or magnetism things. So they used these words, the permittivity of free space and the permeability of free space. Now it was eventually discovered that no, there's no such thing as the ether. Outer space is empty. So these constants kept these names, but they had been figured out their values. So even though they have these names that don't matter anymore, they're usually introduced. So values. Mu naught has an interesting value. It's 4 pi times 10 to the negative 7th. So 4 times 3.14 times 10 to the negative 7. So let's see, that's it's about 12 times 10 to the negative 7. So it's about 1.2 times 10 to the negative 7. But its exact value is 4 pi times 10 to the negative 7. And it has very funky units. It's measured in Tesla times meters per amp, or a Newton per amp squared. And you could go back and chase that out through here. We need to get an answer in Tesla. Well, this is a charge times a meter per second. So that gets rid of the amp and adds a meter, but then we divide by meter squared. And so that's unit-wise, this magnetic field does end up being a Tesla. Before we move on, I want to point out something else about these 2 old constants. So the permeability of free space is this. Remember that the permittivity of free space, epsilon naught, was 8.85 times 10 to the negative 12th. I also remind you that K is equal to 1 over 4 pi epsilon naught. Isn't that interesting? 4 pi shows up in both places. Well, now I want to do a numerical thing. If you multiply mu naught and epsilon naught, so I'm going to multiply them. So 4 times, let me use my pi button, clear, 4 times pi times 1 EE negative 7, and then multiply by 8.85 EE negative 12, I get 1.11212 times 10 to the negative 17th. And then I'm going to take the square root of that. and I get 3.335 times 10 to the negative 9. And then I'm going to take the reciprocal. And I get 2.9986 times 10 to the 8th. That number should look familiar. We've talked about this. This is rounded 3 times 10 to the 8th. And the units are meters per second. 1 over the square root of these two weird constants based on free space is the speed of light in vacuum. So we are leading up to the last day of this course is Maxwell's laws of electricity and magnetism, when electricity and magnetism were put together. But here's your first hint. Electricity and magnetism put together tell us the speed of light, because light is an electromagnetic wave. So it's a bit of a preview of things that are coming. Now, I showed you this source equation, magnetic field made by a moving point charge, and you're going to do a little bit with it. But it's actually pretty hard to get individual charges to move in the vacuum. We have to build these huge particle colliders, and so the magnetic fields they make, because they're not very strong charges, are pretty weak. So if we want to have some significant magnetic field, we do wires. So if we have a long, straight wire, the magnetic field is given by mu naught times I over 2 pi r. So mu naught, you know the value of the new constant. The bigger the current, the more magnetic field. The closer you are, the less magnetic field. And notice it's a 1 over r dependence. I do want to remind you, back with the electric field of a point charge was r squared, and the magnetic field of a point charge is r squared. The same thing happens with electric field and magnetic fields for a long line. A long line of charge was 2k lambda over r. So again, the farther away you got, the less field, but it's not r squared, it's just r. Now you might be thinking, okay, this constant is 4 pi times 10 to the negative 7th, and this is 2 pi, why don't we do some canceling? You will numerically, but in general it's written this way, and this equation is not on the College Board formula chart. We are going to talk about how to remember it and get it with Ampere's law in a couple of days. So for now, you just need to know this value. And I forgot to box this one. I should have boxed this one. You need to know this equation. But now let's talk about direction, because I didn't put any vectors on here. So if you have a wire, and I'm going to show you a physical demo of this. If you have a wire carrying current, and you put a bunch of compasses around it, compasses detect magnetic field. What you will see when you turn on the current is that if the wire is pointing, let's see, use the point, if it's pointing straight out of the page, you are going to see the compasses all pointing in a circle around the wire. So the magnetic field along a long straight wire looks like circles. So I could draw this. So if I have a current carrying I out of the page, I'm going to get circles around it. Well, there's another right-hand rule. Some of this is the same. The current is still your thumb. The magnetic field is still your fingers. But you're not going to lock your hand in position. You're going to curl it gently. Point the thumb out. Keep that straight. But your fingers curl around your thumb. So if you point your thumb out of the page, I get a circle pointing in the direction of my fingers. So if I put my thumb right on that dot, I see my circle is going counterclockwise. So there's a magnetic field going counterclockwise. And it extends through space. It just gets weaker as it goes farther and farther out. So, but again, the way I got that with the right-hand rule, you point your thumb in the direction of the current, your fingers curl in the direction of the magnetic field. So I could also do this for a wire that's lying on the paper carrying current in this direction. So if I point my thumb this way, I can see I get circles that go around the wire like this. That's really, really hard to draw. So all we're going to draw is where the magnetic field actually intersects the paper. So all those circles go into the page on this side, they go down into the desk, and they come out on the other side. So I'm going to draw an into the page here, and an out on this side, and an in, and an out, and an in, and an out, and an in, and an out. Just like on this picture, they would have been stacked higher as the wire extended. On this page, so this is like the side view. And then, as you go farther out, there's less and less magnetic field, but same direction. So everywhere on this side of the wire, I drew that whole thing backwards. Oh my goodness. Everywhere on this side of the wire, they're going into the page. Bad teacher. Everywhere on this side of the wire, they're going into the page. X, 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 and every side over here, they're coming out of the page. Dot, 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 and then set and continue. But I drew that backwards. Shame. Don't look at that. So new right-hand rule, but in many ways easier. You already know the thumb assignments, and you don't have to hold your hand, and there are not as many permutations. So in and out. Shame. Shame. So there's one more object we need to talk about, and that is called a solenoid. A solenoid is a long coil of wire. So essentially what I want you to picture in your head is a slinky. So if I were to draw it, I would have this. So the magnetic field from a solenoid, the magnetic field of a slinky, and this is the lab we're going to do, is equal to that same constant, mu naught, keeps showing up, times a new number, little n, times I. So the more current, the more magnetic field. That makes sense. This constant shows up. N here is number of coils divided by the length between the ends. So for example, let me just draw 5 coils. So if I draw 1, 2, 3, 4, 5. 1, 2, 3. Yeah, that's 5 coils. N here would be 5 divided by, sorry, need to go get a ruler. This is 3.5 centimeters, which you could convert to meters. But if I compress the slinky, same slinky, I just push the coils closer together, this would be N divided by 5 coils divided by only 1.5 centimeters. So it's not the length of the wire used to make the solenoid, it's how closely spaced the coils are. So N is called the coil spacing also. So number of coils divided by the length between the ends of the solenoid. And yes, you would usually change the centimeters to meters and all that stuff. So when we do the lab in a couple of days, what you are going to test is this equation true? So we're first going to test the current. As we get a bigger and bigger current, what happens to the magnetic field? And you should see it not only increases, but it increases directly proportionally, because doubling the current should give you double the magnetic field. And there should not be an intercept. When the current is off, the magnetic field provided by the solenoid should be 0. Then you're also going to do number of coils. That's why we're going to use the slinky. You're going to have a fixed number of coils, and you're going to have them, I think I have you start with them closely spaced, and then you spread them out farther and farther and farther and farther. And so as the spacing goes down, you should see the magnetic field goes down, directly related to this equation. So it's a good lab, it just has a lot of setup with it. But this is the third and final magnetic field calculation, source calculation you need to know. All of these end up with units in Tesla. So that's it.